So user-defined functions and apply. So since you all are intermediate R users, you've probably used the apply functions before. So I'm going to go over what they individually do in just a second. But what they're normally used is to run a function for all the columns or run a function for all the rows individually. Excuse me. So they are very intensive. So base R in general uses a lot of memory and processing power. If you use apply on a 2 million row data set for base R, I don't know how long it would take, but it also might crash your computer or crash your R session because it's going to use a huge amount of memory and it's going to take a really long time for it to go through each individual row by itself. So what I'm going to show in the last thing that I'm going to show is parallel processing using apply. The next class is looping, and there's also a parallel processing way to do loops. And I'll show that next week. So what is parallel processing? If you use the base R apply functions, it's going to run each individual row at one at a time. So when it finishes the first row, it'll move on to the second. When it finishes the second, it'll move on to the third, so on and so forth. So parallel processing runs multiple rows simultaneously. So my computer has 4 cores. I'll show you how to find out how many your computer has. My one at work has 8. So the recommendation is to use one less than the available cores. So say you have 4 and you were running on 4. It would run 4 rows simultaneously. Then once it's done with those 4 rows, it will move on to 4 more and 4 more. So it should run much, much faster because it is processing those all at the same time with the different cores. So how you would set this up. Like I said, the rule of the thumb is to use the number of available cores minus 1. This is in the parallel package, which you should have installed in the beginning. It's actually in base R, but you have to load it. So we're going to use this detect cores, and we're going to subtract 1, and then we're going to set that to number of cores. Then down here, we're going to start a cluster. So that is what the parallel processing is working on. So we're going to make a cluster with, in this case, I'm going to show it's going to be 3 cores because that's what my computer has. And then when you're done with all of your code, make sure you stop the cluster or you're going to be using a lot of processing power, even though you're not doing anything. So then just a real quick recap of the apply functions. So the apply in base R, you can use it to run on rows or columns in an array or a matrix or a data frame. So it will run for each individual row or each individual column based on what you tell it to do. lapply will work on a vector or a list, and then it will return a list. sapply works over a vector or a list and returns a vector if possible. It will return a matrix too if that's the best way. rapply runs a function by rows of a data frame or matrix. It'll work a little faster than apply, just because specify what you're doing in particular. So the parallel package here has apply versions that will run in parallel. So cluster apply is the same thing as apply, or it does achieves the same goal, just on with parallel processing. lapply is pair lapply, pair sapply, and pair rapply. Those are the particular functions. So I'm going to go in, just like I said, there was a cheat sheet for per, there's a cheat sheet for parallel computing. You can definitely use this. It's also in the shared drive. As we get to more complex things, there's a lot of really useful cheat sheets, and I'll be showing them. So I'm about to show this, but I want to show you the TEDS flags. I'm going to move this all the way over. So head TEDS flags. So we're going to look at the top 6 rows of this. So we're seeing here that this has subsetted the data to flag variables. So each individual row is a admission. And so in this first row, the only thing that they had in their system was alcohol. So we would count that as a 1 in that case. So we're seeing row 3 had marijuana and alcohol in their system. And row 5 had alcohol, heroin, and methamphetamine all in their system all at once. So that's what we have subsetted the data to. So I'm going to start my cores, so setting that to 3. You'll see the number of cores that -1 is 3 on my particular computer. What I'm going to do here, so I wanted to know for all of the 2017 admissions, how many were done for specific drugs. So this is going to count up all of the column values together, where they're going to sum them, all the ones, and it's going to dump out how often each of those drugs occurred in practice. So we're using parallel S-supply because the best way to do that, to count up an entire column, would be to use this, and it's going to do it in parallel. So it's going to go through each row individually and sum each column. And we're telling it to use the function sum. In a lot of cases, you will want to use more complex functions than sum. There is syntax in order to add, like say you are trying to do some type of correlation model, you'll need an X and a Y variable in a correlation model. So you can put multiple arguments into these apply functions. And you can look at the help menu to figure out how that's done. So this is going to loop through 2 million rows. Pay attention to how long this takes. Already done. It ran on 4 cores, and we're seeing that alcohol has often. We're seeing basically how often each of these happened. So in our full data set, for instance, inhalants happened 2,090 times. That was not real common, but alcohol was. So it went through 2 million rows in probably 1 second. The next one is even more intensive because it's going to go through each individual row and sum each row. So what this would do would tell us how the number of drugs that was in each individual person's system when they walked in the door. We're going to run that. See how long it takes? Still going. And this is much more intensive, but it's already done. So we went through 2 million rows and summed them in probably 3 seconds. We can see what this looks like. So this is just a label. So the first person had 1 drug. The second person had 1 drug. The third person had 2. And the fifth person had 3. That's what we saw earlier when we looked at our entire data frame. So I was interested in saying, what is the maximum number of drugs that any individual in the data set had in their system? 1. So we're just going to look. It was 3. The largest number of drugs that were simultaneously in somebody's system are 3. So now that we're done with that, we want to stop the cluster, and that basically just means we're going to use less processing power within R. So I wanted to show you guys that because I, at Whole Foods, use a ton of just gigantic data sets. Within R, the largest one I've used so far, and this is because I paired it down with SQL before I ever even got it into R, was 14 million data rows. So when you're using that, if you don't use the parallel processing functions, your computer will not be able to handle it. The RAM and processing power will go up so high that it will usually crash your R instance. So one other thing I would recommend looking at, I believe it's the FF package. So packages for parallel processing. So there are a couple here. The main one, FF, is really good for database work. So when you are pulling a large a set from a database into R, the FF package works really well because it pulling from the database is not the memory intensive part. Writing the database file to an R dataset that takes forever. The FF package writes it to a dataset that is spread out within usually 5 or 10 different datasets. So it's stored separately on the back end. So it loads on your computer a lot quickly and processes them in parallel. Another one, Big Memory, is another parallel processing package that is useful. It's good. It's faster than FF, but the downside to it, everything has to be a matrix of numeric values to use this. So it would be useful for machine learning, because when you're using machine learning, everything has to be numeric anyway. And they actually have some machine learning functions in there. I believe k-nearest neighbors is in Big Memory. And another one that we used today was the parallel. So that's a really great one as well. So those are the main ones that I've used. This one is the most useful for database work. Parallel has a lot of really useful things. So when you're going through, if you, like many other data scientists, work with large data sets, I would recommend trying to use these because it would be really helpful to you.